Thanks a lot for invitation, and also today my talk is about the singular kinetic equations. This talk is based on joint work with Zimo Hao, Xicheng, Zhang, and Xiangchan, and the reference for my talk is read on archive. Here, this is first we go to the background and the motivations for my talk. In fact, our motivation comes from this mean field limit. If we consider the following second order interacting particle system, and here we consider this xi will denote the position, and vi the velocity of the ice particles, and this SDE will in fact denote the this interacting particle system. And in v directions, we also have the driven noise, which just gives by the independent of Brown motion for each particles. And you could view this B as the random environment depending on this position and velocity. And here this K is just some interacting kernels between different particles. So here we have the interaction for ice particles. So we have the interaction from other particles, and we just K the interacting kernel. We take the summation, and here we have extra 1/n. This is to balance with here we have this summation for n component, and in this case when n becomes larger, we could see the interaction between different particles will become weaker, and if we just suppose each particle is independent, n becomes larger. In fact, this kind of equations we're using the law of large numbers. This just gives us we could give the mean of this arrival xtj part here. So in fact, this suggests us to obtain the following distributional dependent SDE. Also, this is so-called this marking velocity equation. And for this kind of SDE, if we consider in this case, we just write the expectation in terms of the law of this xt here. And for this case, if B and this kernel K is smooth, then we can easily get the global well-posedness for this interacting particle system, and also the related limit. And also the related so-called this propagation of chaos hold. That means the limit this convergence will hold, and this convergence also tells us if we consider this interacting particle system for each particles for fixed n, they are not independent of each. For different components, they are not independent, because even the initial data is independent, but for any fixed time t, they have interactions between different particles. But when n becomes larger, that means the number of the particles becomes huge. Then we can see the limit will not influenced by the other particles, so they will become independent. So this is so-called this propagation of chaos. And in this case, we also want to see, because this SDE also depending on the law of the xt, if we're interested in the law of this xt, and also consider empirical measure, the limit of this empirical measure of this xti and vi, we will get the following kinetic equation written in the following way. We could see here, since the driven noise only comes when only have in this velocity part, so we would give the Laplacian operator only in v directions, and for the x directions, we would get this transport term v times this gradient of this u here. And this k part just comes from this distribution dependent, and this k only depending on the position. So here, this the bracket of this u, we were taking the mass with respect to this v. We just take the integral and obtain the limiting equation written in the following way. And for this kinetic equations, we can see this, and if the divergence of this B equals to 0, we could obtain the following equations. And our problem is if we consider this B is some like the random environment, for example, like the special white noise or some Gaussian free field, in fact, B is very singular. And also for some interesting model from physics, this K is also singular. Whether we could obtain the global well-posedness of this kinetic equations for this singular B and K, and also the global well-posedness for the distribution dependent SDE. And in this case, and this SDE depending on the law of the solution and time t. So if we study the Martingale problem, this will satisfy some nonlinear Martingale problem. And in this case, if we consider these linear operators, in general, we consider the Kinetic operators. But in this case, for the Laplacian, we only have the Laplacian operator in y directions. And this is just like, it's not an elliptic operator, just a hyperelliptic operator in this case. And now I want to consider this. First, we just give some basic knowledge about this kinetic equation. We just consider this linear kinetic equation. And here, this V, as we mentioned, it denotes this velocity. So we could not consider the we have some cutoff properties. So we need to consider V on the whole space. So this is also we consider our problem on the whole space. And here, this the sign, this plus or minus, just corresponding to the Kolmogorov equation or Fock-Planck equation. So this will not influence our analysis. And if we consider these kinetic equations and do some scaling to understand the scaling for this kind of linear operator, we just do this scaling transform to replace this U by this U lambda with the following scaling transform, and also F to change F to this F lambda. If this U lambda and F lambda should satisfy the same equations here, then we could either calculate this A, B, and C should equals to these values. So from here, we could see the component for this X, this lambda to approach C, is also different from this V part here. And if we consider the shorter estimate for this kinetic operator, in fact, since in y direction, we also have this Laplacian operator, so we could still gain two regularities in y direction. But if we consider the in x direction, due to here we have this transport term here, so we can still gain 2/3 regularity in x direction. So this also from the scaling properties, the scaling of x and v, in fact, is 3:1. So this will suggest us to study this problem in this anistrophic Besov space. And here we just define this C alpha space in this with respect to this anistrophic metric. So this means for this x direction, so we have this extra exponent 1/3. And also for this V is the Euler metric. And in this case, for this holder norm, so we just consider with respect to this with respect to this anistrophic metric. This is this anistrophic holder space. And in this case, we could also write the solution to this linear equation explicitly by using this kinetic semigroup. If we this could be written explicitly than before. In fact, this small pt is just the density for this Brown emotion and the integral of this Brown emotion part. But for the kinetic equation, the related semigroup cannot be written as this just a convolution operator. They need another transport operator gamma t. So this gamma t just means in this x directions, we have the extra this, we need to plus this tv in this extra directions. and to write this kinetic semigroup in this way. And finally, we could write the solution to this linear kinetic equations by using this kinetic semigroup. Yeah, this is the main difference between this between the heat operator. And by using this, and now we want to consider the following nonlinear kinetic equations. And as we mentioned, we have in mind for this example for this B, the special white noise. But now we have considered everything on the whole space. If we analyze the properties of this B, the pathwise property of this B, on this whole space, this will not stay in the Euler holder space. First, it's a distribution, just stays in some say minus alpha space. Here, alpha, we just assume this alpha bigger than 1/2 and smaller than 2/3. And here, this B for the infinite volume, it also stays in this weighted Besov space. That means for the pathwise property will allow this B have some growth at infinity. And also for this F, we also allow to have some growth at infinity. And here the regularity for this B is bigger, is in this say minus alpha space. If we calculate the regularities, in fact, by Schauder estimate in this anistrophic space, the best regularity is also this say 2 minus alpha space. But if we want to make sense of these blue terms, this will meet similar difficulty as what we have done for singular SPDE. And because if we consider, if we want to define a function times the distributions in the say alpha and say beta space, we always need this alpha plus beta bigger than 0. This difficulty will always meet. So in this case, we also need to use in this regularity structure theory or this paracontrolled distribution method to solve this problem. And in fact, in this talk, our aim is just to develop this paracontrolled calculus to get the global well-posedness for this kind of nonlinear kinetic equations here. And in this case, we just first consider this linear equation. So linear equation just means here the interaction kernel just equals to 0. We first want to get some Schauder estimate for this linear kinetic equation. So we just recall the equation as here. This is our kinetic operators. And here this B and F is also distribution. So we want to develop this paracontrolled calculus in this kinetic setting. And in this case, we first introduce this kinetic holder space. As for this kind of kinetic equations, if we this kinetic holder space is our solution space, and we want to do some Schauder estimate for it. But in general, the solution space, we need the solution have say alpha holder regularity with respect to space, and also say alpha over 2 regularity with respect to time. But in this case, since this kinetic operator and also kinetic semigroup involve some transport operator, this gamma t, we have this translation along this x direction. So for this space, in fact, we change this definition of this holder space if we want to consider the time regularities. In this case, for this, if we just calculate this ft subtract with compare with fs, we just need extra this gamma t minus s before this fs part here. And for this kind of the reason to introduce this gamma t is still comes from the structure of this pt. In fact, pt just can be written in the following way. And here, this small pt is a convolution operator. We could only do this Schauder estimate, in fact, for these convolution operators. So in this case, so we need to add extra gamma t here to do this time regularity estimate. Another thing is if we want to just compare this gamma T F and F, just using some code regularity from X directions. In this case, if we want to get extra T to the power beta, we will also get some extra V here. But this V part will always requires, if we want to control it at infinity, we need to use some weight from this zero here. So this is not good enough. So in this case, we want to do the shorter estimate, stay in the same weighted Besov space. So we consider this time regularities we introduce using this gamma T here. And in this kind of state space, we could get the usual shorter estimate for this kinetic semigroup. And furthermore, we want to still using this paracontrolled method to analyze the equation. So we just recall for the paraproduct, if we want to define this F times G, for F is a function, G is a distribution. That means we could have the following three decompositions. This blue term is just the bad term, and this red term is well-defined if only if this alpha plus beta bigger than 0. And this term is always good and don't need this condition. So we're using this paracontrolled decompositions, paraproduct decomposition to decompose this terms, because this B times this gradient V gradient U part is a singular part. And now we're using this paraproduct to write it. And here, as B is very singular and U have better regularities. So this blue term, this one is just the bad terms. The regularity will not better than the B part. And the red term is not well defined in the classical sense. So we need to make sense of this red term. And here, to make sense of it, we need to using this paracontrolled ansatz. Just assume this solution of this U could be written in the following way. That means from here we see that the bad term that on the right just given by this blue term and also this F. So if we want to, we could write the bad terms on the right, just this term corresponding to the blue term, and this IF corresponding to this F part. And we think this U sharp should satisfy the following equations. So these two terms corresponding to these two ones on the right, and this blue terms is the commutators for this the inverse of this L. Just so if we could obtain these two terms by the paraproducts, will have better regularities. If we could get this one have better regularities, this commutator have better regularities, then this U sharp will become a regular term. And if we substitute this paracontrolled ansatz to this red terms, by the original paracontrolled this commutator estimate, we could make sense of this red term. So our aim is first we need to prove this U sharp have the better regularity. So we need to prove a commutator estimate for this kind of I operator related to this kinetic operator. In the original paracontrolled paper, they have proved it for the heat semigroup, and now we just developed it for this kinetic semigroup. And in this case, here this PT is, as we just recall it here, this is our kinetic semigroup. And as we recall, this paraproduct F smaller than G, this paraproduct, we cannot gain any regularities from this F part. The regularity is always the same as G. But if we subtract these terms, subtract, it's like a commutator, subtract this F smaller than this PTG. Then if we take in the little the Paley block, we could see we could get extra 2 to the power minus alpha j here. This means, in fact, we could get the alpha. We could get some regularities from f here. So this will give us this commutator estimate. And here I also want to mention this red term here, this gamma t. In general, if we consider this for the kit semigroup, if we want to prove this commutator estimate, we don't meet this gamma t. But for the kinetic part, we have this transport operator. For this transport operator, we just leave it here because we could not prove this commutator also holds for this gamma t. We could not move this gamma t to here. So we just leave it here. But this is already enough for us to prove the required this for the related semigroup, the commutator estimate hold. And we can gain some regularity from this F part. So this will give us this U sharp will stay in a better space. And if furthermore, if we assume this B satisfies these two conditions, and for this F, by usual this pair product, this commutator estimate, and this pair controlled ansatz, we could make sense of this red term, this B circle, this gradient U part here. And here, in fact, we consider if B is just deterministic and stays in C minus alpha space, we just calculate the regularity. It should, we also, for alpha bigger than 1/2, it's still also not well defined in the classical sense. So here we need to do this renormalization. And in this case, we just we first do our calculus under this assumption, just assume all the renormalized terms have been defined in this space. And we just give the examples to check when these two assumptions will be satisfied. So if we suppose this B is just a Gaussian random field with the covariance operation given by a spectral measure, this mu here. And here we assume this spectral measure is symmetric in the second variable and satisfies some integrability condition. Then by the probabilistic calculation, this B will stay in this C minus alpha space. And also this pair product also stays in our required space. And our examples, if we consider this mu just be written in the following way, in one-dimensional case, we could cover the noise in which is white in y direction, but still colored in x direction. Because in x direction, we could only gain 2/3 regularities. It's still very weak, so we could only do it for colored in x direction. And the interesting point is, as in our case, for this kinetic part, we also don't satisfy this translation invariance property as Ivan has mentioned. But if we, but we only need to deal with these terms. This is like stays in the second order. If we're using the Wiener-Chaos decomposition, just stays in the second order Wiener-Chaos decomposition. In the second order Wiener-Chaos part. And in this case, if the usual renormalized terms, renormalization constant or some divergence part comes from this zeroth Wiener-Chaos part. But in our case, this zeroth Wiener-Chaos part is also not a constant. But it will be a function depending on this v variable. But if we subtract some formally divergent terms, this will converge in this, still in this space. But this formally divergent term, in fact, it's 0 by using symmetry property. In fact, we assume this mu is symmetric with respect to the second variable. And here we also have the gradient in y directions. So if we calculate by using Fourier transform, we would see some odd functions will appear in the calculations, which is 0 by symmetry property. So for the renormalization, so we would say if we consider approximate equations, we would not we would say there's no renormalization, any renormalization constant or renormalized terms appearing in the equation. So for the approximation equations, it just looks the same as the usual equations. So this is for this renormalization, and now we just consider for the well-posedness for this this linear PDE. And here the main difficulty part comes from this B part. And our main result is we assume this B and F at above, then we could obtain this solution U, and this U sharp will satisfy this Schauder estimate. And of course, this, we could also obtain the existence and the uniqueness of the solutions. And the idea of this solution proof is also based on this paracontrolled calculus we developed before. And we also need to handle this weight problem here. If we consider this nonlinear this linear terms, here this B will stay in the weighted Besov space. If we're using some like this calculate some C alpha rho norm, this B will always take out some of the some part of the norm. And this will stop us to using the Grom's lemma and the fixed point to obtain the solution. In our case, we just using the idea from our previous paper for the singular HJB equations. We first consider the Schauder estimate for B and F stays in the unweighted Besov space. But here, in fact, we're using a trick to first introduce a damping term lambda u on the left, and finally we could obtain this Schauder estimate with depending polynomially on the coefficient, not exponential growth. And then we consider the Schauder estimate with the coefficient in the weighted Besov space. And here we're using a localization trick. So this means we just multiply some cutoff function on the both sides of the equation. And first using this result in the unweighted Besov space. And using a characterization of this new characterization of this weighted Besov space, we could obtain this kind of result, Schauder estimate. And for the uniqueness, we also using this localizations techniques. That means the paracontrolled solutions to this linear PDEs with the coefficient in the weighted Besov space. If we using the cutoff functions, U times the cutoff function is also paracontrolled solutions to the equations with the coefficient in the unweighted Besov space. So we're using this kind of calculation of this localization to obtain the uniqueness. So this is for the well-posedness for the linear case. And now we come to the nonlinear case. For the nonlinear case, in this case, we just have this interaction kernel K part. And K is do the convolution with the integral of this U part here. And here we just assume this K have better regularity than this B part. So in this case, for this nonlinear term, we will not meet the problem for this not a well-defined problem. And for this kind of, as we mentioned before, for this nonlinear equation, in fact, this gives the law of the SDE. So we just want to find a probability density solution. So if we consider the solution, if the initial data U0 is the probability density, satisfies some regularity. But here we also need the initial data stays in L1, but allows, but it will satisfy some decay property at infinity. I will explain this later. Then we could find there exists at least a probability density paracontrolled solutions to this nonlinear mean field equations. And in addition, if this K is bounded and the entropy of this solution, the initial data is finite, then the solution should be unique. This is our main result for the global existence and uniqueness for this nonlinear mean field equations. So in general, for this nonlinear PDE, if we want to get global well-posedness, we need some uniform estimate. But in general, it's very difficult. But in this case, since here this nonlinear term is given by this convolution operator, and U is the probability density. Probability density, so it always stays in the L1 space. By the convolution approximation, or by the convolution estimate, this one stays always in this C beta space, in fact. So this will gives us automatically priority estimate from the linear equations. However, this is not enough for our use because our nonlinear term involves this non-local term, this k, do the convolution with respect to this u part here. For this, if we want to prove the convergence of these terms, we need some L1 integrability for this for the solution u here, but here our shorter estimate always to make the solution is only local. It's like we only have the shorter estimate in this weighted Besov space. So this means we allow the growth at infinity. So this is not enough to deduce the convergence of this non-local term. So instead, we're using another method. This is also the reason we assume this initial data have this L1 integrability condition. And we could prove the solution ut, and anytime t can be controlled by the initial data, the L1 norm. But here, this weight is some decay weight. This means this is some growth weight. This means the solution, this means the solution should have some decay property at infinity. And to prove this kind of estimate, we're also using the SDE method, because here this is ut is the probability density for some SDE. So we could just write it in terms of this SDE. So Zt is the solution to the related SDE. And to estimate this zero Zt, we just using Ito's formula to write it in this way. The main difficulty part comes from these red terms. And for this red term, this is we're using like the Krylov estimate to using the Ito's formula to write this red terms in terms of the solutions to the following backward PDE, this WT. And this WT is just the solution to the backward PDE. And we could using the solution of this WT to express this integral. And even this B and K is singular, but by our result of linear PDE, we could see the WT have better regularities. So this will give us how to control these terms. Finally, we get the uniform estimate for this UT. This gives us the existence result. And for the uniqueness part, we just take the difference between two different solutions. But here the solution U1 and U2 just stays is a probability density. And here we also need to involve this convolution operator. So we just consider prove uniqueness in L1 space. To handle these terms, we also need better regularity estimate and integrability for this gradient of this U1. So we need to do the estimate to get better regularity for these terms. Our idea here is to use this entropy estimate. In this case, if we consider this beta U equals to this entropy of this U here, and we formally just calculate the derivative of this beta U, we could say we just like times the the derivative of this beta on the both sides of the equations. But for the Laplacian part, we will get extra these terms. And for the other terms, it's related to the derivative of this beta here. And here, since this beta is the convex functions, so we could the second derivative always be positive. So we could always put these terms on the left. So if we take in the integral in a1 space by integration by parts formula, all this the first three terms on the right should be equals to 0. And these terms will give us these dissipations. So finally, we could easily get this entropy estimate. This is our what we required. However, when we do this estimate, we will meet these red terms. This is just the formal calculations. If we calculate the regularities, we will also meet the not well-defined problems. Since if we calculate the regularity, the derivative of this beta is this two terms is we cannot multiply these two terms. So in this case, we solve this problem. We consider linear approximation for this U1. For fixed U1, we consider this kind of linear approximation, and this UN will convergence to this equation to this U1, and we just do this entropy estimate for this linear approximation, and obtain finally by taking limit, we could obtain the U1 have also satisfy this required estimate. Maybe I just have maybe 5 minutes, right? Or no? Just for the last. Last part is about this distributional dependent SDE. Maybe I just talk about this distributional dependent SDE part. And this in this case, it's also SDE with a very singular drift B here, and also depending on the the law of this x and time t. And in this case, since this B is singular, how to understand this SDE is a problem, because if B is a distribution, we don't know how to say the distribution composed with a function here. And we could also consider this Martingale problem. If we consider the Martingale problem, we need to write the related generators. This can be written explicitly. But we could also meet this B part here. Even we take this F is very smooth, but B is still a distribution. And also for this one is also distribution. How to make sense of these terms composed with just a process? This should be a problem. And to solve this problem, we just follow the idea in this papers by first. It's been done by this Law and Deal, and also by this Kanjaro and Chalk, and also by Crump and Perkowski. They just consider if we consider mu is given, we just consider the solution to this linear PDE. And we could using the solution for this linear PDE to give the meaning of this Martingale problem. So that means if for any f is a functions, by using our shorter estimate, we could always say this u is a function and f is a function. And the usual Martingale problem is if you compose with ZT and subtract this LU here, it should be a Martingale. This is the usual Martingale, the definition for the Martingale solutions. But here we're using this linear equations to solve this, to replace the LU by this F here. And for given F, we could find the solution, find this solution U here. And this is and U is always be a function. So each term should be well defined. And this is our definition for this Martingale problem. And using this definition, we could say under our assumptions for the coefficient, we could find a unique Martingale solutions. We could first find the existence of the Martingale solution to this SDE. Furthermore, if K is bounded, then the solution should be unique. And the proof first for the existence, we're using the convolution approximation. And for the uniqueness, we first do the uniqueness for this K is equals to 0. That means there's no interacting term. And then as this K is bounded, we could using Besov transform to obtain the uniqueness of this nonlinear Martingale problem. And here, this is all my talk. Thank you for your attention.
Thank you very much. And we have a discussion. Niels, I think.
Okay, yes, so let me see if my video is working. So I'm using Hendrik's iPad. So let me see if I can share the screen. Okay. Start broadcast. So that seems to work, right?
Yes.
Okay, thanks. So, okay, so thank you, Rongchan, for the very interesting talk, and the organizers for the so the opportunity to talk here, and also thanks to Henrik for lending me his iPad. So this is a little bit improvised. So I didn't have time to prepare slides before because of the switch. So what I'm going to do here is to try to give a rather general context on singular SPDEs, because part of the participants here are rather from the physics and renormalization side. So what I'm going to say is maybe more intended to them. So the SPDE specialists will, I guess, know everything I'm going to say. So just to give you some context, in the last 7-8 years, we've had a lot of new and exciting results, and they started with the parabolic SPDEs on the torus. So these are of the following forms. So dt phi is Laplace phi plus some nonlinearity f of it can depend on phi, it can depend on its derivative, and psi is this very singular object we've heard about before many times, which is space-time white noise or some similar very rough objects. And examples, very classical by now examples, are the phi 4D model, for which f is equal to minus phi 4 plus noise. Another important example is the KPZ equation describing surface evolution, and there we are in dimension 1, so f is something like minus derivative of phi squared plus noise. And a third example would be the parabolic Anderson model, where f is equal to phi times psi, but here it's only spatial white noise. And by now we have actually theories for many more equations like that, as long as they are subcritical, which is the same as super renormalizable in quantum field theory. So for this kind of equations, already now very much is known. So you could now ask about extensions. So what kind of extensions can we look at? So there are many possibilities, and in Rongchan's talk we have seen several additional difficulties. So one of them is that it is in RD instead of the torus. So there have already been quite a few results on systems like that, where you go to RD. So, for instance, okay, there's a work by Martin Heuer and Cyril Labbé on the parabolic Anderson model. There are works by Jean-Christophe Murat and Hendrik Weber on 5-4 type models, and also by Augustin Moinat and Hendrik on some more general classes of models. So that's one difficulty, where you have to do something like introduce weighted spaces because of the infinite extension. Or there's also this idea that Augustin and Hendrik used, where you have some kind of spatial coming down from infinity property. So but still, it really depends very much on the model. So in the talk that Rongchan gave, you have to also introduce some kind of weighted spaces, but it's really, as far as I see it, it's very model dependent. So they had to introduce some new spaces for to be able to address that. Another extension that we've seen in this talk is that there are less regularizing differential operators. So instead of having the Laplacian like there, and so the heat semigroup has nice regularizing properties, we had this kinetic equation, which is actually really quite bad because it's like a coupling between an SPDE and an ODE, or it's a second order equation. So part of this, of the general theories, work actually for more general operators, but okay, you don't have the same regularizing properties, and so there's really quite a lot of additional work to be able to derive something like Schauder estimates for those. And another difficulty we have seen in Rongchan's talk is that we had a non-local nonlinear term, so it was this Mac-Vlasov type of nonlinearity. So again, there you need some new tools to deal with those. The side remark, interestingly, in regularity structures, you also have non-local operators popping up. It's this calligraphic N for the specialists. Though I don't know if there's any link between these. Okay, so let me try to explain for non-specialists a few ideas on how in general people go about solving these equations or constructing a solution theory, and where these difficulties come from, and also what's the connection with renormalization. So the general idea to try to solve an equation like the parabolic one I've written upstairs is to say, okay, we create a fixed point operator, so we observe that phi can be written as the inverse of my linear operator times the nonlinearity. So f of phi, nabla phi, and psi. And this guy here would simply be the heat kernel. And the difficulties come, as has been said many times, from the fact that psi here is very singular. So two facts are important here. So what you need, you want to apply some kind of fixed point argument, so you need a function space which will be invariant under this map, and that's the difficulty. So one fact which is used here is that space-time white noise, if psi is space-time white noise, it's almost surely in some Hölder space or Hölder-Besov space of regularity minus d plus 2 over 2 minus. And okay, it's actually with a parabolic scaling. So also in Rongchan's talk, you have seen a non-Euclidean scaling that plays a role there. So which means that it is a distribution. Now, so this is a difficulty. So something that helps is this Schauder estimate, so which in the parabolic setting tells me that if phi is in some C alpha, so also parabolic, I don't write it here, then if I apply the heat kernel, then I gain two units of regularity. So, that was something also different in Rongchan's talk, because they only gained something like, I think it was 2/3 because of this kinetic setting. So what happens if I combine these two things here is that if I apply the heat group to space-time heat semi-group to space-time white noise, then I land in Hölder space of regularity d 2 minus t over 2 minus, and you see that 2 minus t over 2 minus is negative when d is at least 2, which means that even the stochastic convolution, so this object is not a function, it's a distribution, and then you have problems in defining things like its square or its cube. So this is where renormalization comes into play. So now let me see, how do I change? I'm not used to this program. How do I change page? Just a sec.
You just move upwards, I think. Just very fast, and then the new site, new page is created.
Doesn't seem to work.
And maybe you click on the new page sign, maybe on the right.
Yeah, I guess there must be something. That's not that.
If you click on the left-hand side on this 4 corners, left upper corner,
okay,
and then you can click the plus.
Okay,
that's it.
Plus,
usually you can just scroll, but I think the presentation, yeah.
Okay, I changed the squares for something else, but it's not important. Okay, so since this conference is about renormalization, let me just also stress the link here. So why do we need to renormalize in general? So actually the simplest way I know to understand this is so let's just look at the stochastic heat equation, which is forced by space-time white noise. So I have this equation here. So okay, the solution will be given by phi is given by dt minus Laplace, so the heat kernel applied to psi, and here you can just write everything in Fourier. So let's expand the solution in the Fourier basis. So the EK are Fourier modes, and so minus Laplace EK that's given by plus lambda k EK, where lambda k goes like k squared. So if I write this in Fourier, everything diagonal becomes diagonal. So phi k dot will be equal to minus lambda k phi k plus psi, and then that I can solve. So it gives me an Ornstein-Uhlenbeck process. So, and in particular, I can see that as time goes to infinity, phi k of t goes to actually a normally distributed random variable. So with a covariance, with variance 1 over lambda k. And so actually phi will be given by the sum over k of, so zk over square root lambda k ek, where the zk are IID Gaussian, centered Gaussian of so standard Gaussians, and that's nothing but the Gaussian free field. So let me ignore the zeros Fourier mode, which we have to treat differently. And now let's see what happens if we want to compute the square of this. So okay, that will be given by a convolution, sum over k phi. So the case part, case component of the convolution ek, and the problem comes from the term k equals 0. So for k equals 0, I have convolution of phi with itself, the zeroth mode, which will be the sum over k phi k squared. So which will be the sum over k z k squared over lambda k. And if I take the expectation of this guy, I get sum over k 1 over lambda k squared, so which goes like sum over k, so sorry, that's 1 over lambda k, and then so that goes like 1 over k squared, and then you see that this is finite in dimension 1, and it's infinite if I'm in higher dimension. So that shows you already why you cannot define the square of this object, but it also shows you that actually in this case it's relatively easy to cure because of translation invariance. You can just subtract a term. So actually what you do is you can make a regularization and then you subtract, so you get here a divergent counter term. And if you subtract that, you get something which so you can define this square. Now let me also make a remark that this is so like this. So there's a link between this and something which is called almost sure improvement. So almost sure improvement of Sobolev embeddings. So if I have a Fourier series like that, sum over k phi k e squared, yeah, phi k e k, and I define the Sobolev. What is this? Sorry. So I have here. So I define the fractional Sobolev norm in the usual way. So sum over k k to the 2s phi k square, where this is the Japanese bracket. So that is square root of 1 plus norm of k squared. So we have the usual Sobolev embedding. Let's say we are in dimension 1. That tells us that h1/2 is continuously embedded in LP for any finite p, but that is false for HS with s strictly smaller than 1/2. Okay, so however, in the random case, you gain something. So if I have my phi, which is has a Fourier expansion like that, and with phi k, let's say, which is given by zk, which are independent standard normals divided by square root lambda k, and like this, then since these Fourier modes are rotation invariant, what actually matters is, so you can see that phi, if you consider these as Gaussian, as complex Gaussian, so they have actually phi of x for any x has a centered normal distribution with a variance which is sum over k 1 over lambda k. And this thing actually, so this thing is nothing but the L2 norm of phi squared. So you see that if we add randomness, actually we don't need phi to be held to be Sobolev 1/2, but actually when it's in L2, you already have something which is which you can make sense of, and that is, I believe, related to what Rongchan called probabilistic calculations. So sometimes you use these probabilistic calculations that allow you to get better estimates on the regularity because you have this this normal distribution. All right, so I've given a bit of an idea of how you can renormalize the simplest possible term, but then if you iterate your fixed point, as we have seen in many other talks, we get actually many more terms, and that's where things really get difficult because we have to organize these somehow. And then there are at least two theories which allow us to deal with that. So there's regularity structures introduced by Martin Heyer around 1314, and there's a power-controlled calculus, so introduced by Gubinelli, Imkeller, Perkowski, about at the same time. And okay, at first sight, these two approaches seem rather different. So it's different ways to control all the the combinatorics that appears when you have to try to define these products of distributions properly renormalized. However, there are links between both. By now, there's some dictionaries. So there's work by Ismail Bayel and Masato Hoshimo, and I think we're going to hear more about that tomorrow. So these two approaches are actually not as different as it might seem. So that was kind of the overview I wanted to give. So let me finish with a remark on something which is called Dean's equation. So I heard about that from a colleague at my lab, Julien Barré, who's interested in the Mekin-Vlasov system. There's actually, so let me just take a Mekin-Vlasov equation, as we have seen here, so a mean field model of interacting particles. But let me, for simplicity, just forget about the singular drift term, forget about, and also let me take a first order equation. So actually, I just take non-interacting Brownian particles, and I have my empirical distribution for n particles. So phi n of tx would be given by 1 over n sum I equals 1 to n of delta of x minus wi of t. So as we have seen in Rongchan's talk. Now, there's a purely formal computation that physicists do, and which tells you that, so you apply Ito's formula, I mean, you apply this to a test function, you apply Ito's formula, and you do some integration by parts, and you find a noise term. But what you find is that actually the dt phi n here is given by Laplace phi n plus a term which is really extremely bad, which is 1 over square root n derivative of square root of phi times psi, where psi is space-time white noise. Now, as far as I know, nobody is mathematically able to make sense of this equation. I think there's even a negative result by Lehmann, Konarowski, and von Rennes saying that you can't possibly make sense of this equation because you have the square root of phi here, which is extremely bad. So actually, I mentioned this to Martin Heyer once. I met him in Cambridge, and his reaction was to cringe and to change subject. So it doesn't seem really possible at the time being to treat this kind of equation here. So okay, maybe my question to Rongchan is: have you ever come across this equation, and how do you, in your case, derive this equation, which is difficult, but which doesn't have this nasty noise term here? And that's all I wanted to say. So thanks for all your attention.